Welcome back. So it's no good to know all about power series if you can't assess whether they converge or diverge. So right now we're going to do some powerful tools, in particular the Cauchy's root test and the Cauchy-Hadamard test that will help us assess whether these series converge or diverge. I want to remind you of the most important sort of quintessential example of an interesting series. This is the geometric series, the summation n equals 0 to infinity of r to the n. It converges is if the modulus of r is less than 1, and it diverges if the modulus of r is greater than or equal to 1. This is basically the series that we understand the best. And in a way, both the root test and the Hadamard test, or the Cauchy-Hadamard test, are about comparing series to this series to see how well they measure up. So let's talk about the root test first. Now, I introduced power series, but I don't want to confuse you. This is not a power series. This is a simple series of complex numbers, but these are not functions, right? An is not a function of z. This is a simple series of complex numbers. Now, I want to compare this series to the geometric series and say, is it doing something like the geometric series did, or is it doing something unlike the geometric series? If you were looking at the geometric series and knew the values of the terms of the series but didn't know the value of r, how would you produce the value of r? Well, there are many different ways, if you were looking at the terms of the series, to figure out what was the common ratio between the terms. One of the ways we could do that is we could take the ratio between two terms, right? I could take the 10th term and divide it by the 9th term, or the 20th term and divide it by the 19th term. And I would always get the common ratio r that way. That's going to sort of move us in the direction of the ratio test. But there's another way we could do this. We could look at the 20th term, which would be r to the 20th, and we could just calculate the 20th root of it. We could raise it to the 1 over 20 power, and then that would definitely recover the value of r. And that's the thing, that's the motivation for the Cauchy root test. We're basically going to take the nth term, even though we recognize this simple series of complex numbers is not necessarily a geometric series, and there isn't a constant value r, we're nevertheless going to sort of get at what that value r would have been if there had been one. So let me explain. We're going to do, so what we're going to do is we're going to let C be, we're going to take A, well, let me leave myself some space because that's not the last thing we're going to do. We're going to take an, which is a complex number. We're going to take its modulus because I can't take the 20th root of a complex number yet. I don't even know how to do that. I'm going to take the modulus, after which I will have a real number, and then I'll raise that to the 1 over n and extract the nth root of the nth number. Now, if we are so lucky that the series is geometric, this will simply give us r. But maybe we're not so lucky that the series is geometric, and maybe this computation is not going to give us a constant, but a value that depends upon r. That would, a value that depends upon n. That would make perfect sense. Now, because we're dealing with long-term behavior of a sequence, we're trying to assess whether it converges or diverges. We don't so much care about the first 10 terms. We don't care about the first 100 terms. What we care about is the last infinitely many terms, right? And so what really is important here is not the behavior of the first few terms, but the behavior of the last infinitely many terms. And so we're going to take the limit of this. But even the limit of this might not exist, right? If I simply say, take the limit as n goes to infinity of this, well, maybe that limit doesn't exist. And so maybe that doesn't really help us at all. And so what we're going to do is we're going to take the lim sup of this. So let me rewrite. We're going to take lim sup as n goes to infinity of this thing. Let me remind you what lim sup means. The lim sup, or the limit supremum, means the largest limit of any subsequence of that stuff. So basically what we're saying here is some of these numbers might be big. Maybe the even terms are large. Maybe the odd terms will give us small values. Take the limit of the even terms in that case. Maybe every 10th term is large. Maybe the other terms are small. But then take the limit of the every 10th terms, for example. So this is going to be the largest subsequential limit of that, which is basically the worst case scenario for the behavior of an, modulus an to the 1 over n. We're going to take that. Now, if we do that to a geometric series, we will simply get r. It will in fact be a constant series in that case, and we'll take the lim sup of a constant and we'll just get the constant r. But if we do it to some other series, then we'll get some other interesting value. But because the lim sup is either exists or equals infinity, then we can say that we can refer to the value of C one way or another. So if we should do this, and we should be in the lucky case that the value of C is less than 1, then what we can conclude from this is very much like this case, that's convergence. So then the series AN converges, and it not only converges, it converges absolutely. But if C is greater than 1, then this series diverges. Now you might think that I'm not done writing because I have to give you one more case. What if C is equal to 1? And the fact is, I'm not going to give you that case because that's the hardest case of all. If C equals 1, then this test is not going to actually reveal the answer to whether it converges or diverges. And so I don't really have anything to say about that, right? If the theorem says nothing about the case C equals 1, then you can't conclude anything. That means it's inconclusive. Okay, let's see about a proof of this. Well, so here we have the lim sup of an to the 1 over n, and we're going to break this into two cases based on whether C is less than 1 or greater than 1. Let's work first on the case when C is less than 1. So let's say proof. So the first case, C is going to be less than 1. Now, if a lim sup, so let's say what that means. The lim sup of absolute an to the 1 over n is less than 1. Now, the lim sup is the highest possible limit of any subsequence of this thing. And it's strictly less than 1, which means that no subsequence converges to 1. And in fact, no subsequence converges to any of the numbers between this value and 1. And that means that if I split the difference between this lim sup and 1, and choose a number in between the lim sup and 1. So let's let S be in the reals so that the lim sup of an to the 1 over n is less than S, which is less than 1. If I split the difference between the lim sup and the 1, then no limit converges to S, no limit converges to anything higher than S, no limit converges to anything even in the range between this thing and S. And that means that there are only finitely many terms of this sequence, absolute an to the 1 over n, which exceed S. If there were infinitely many terms that exceed S, then we would have some sort of lim sup greater than or equal to S. So that means that only finitely many terms, only finitely many n, have absolute an to the 1 over n greater than S, greater than or equal to S even. Only finitely many n have that. So let me say for most n, but what I mean by most is all except finitely many. So for most n, and here what I mean all but finitely many. So for most n, what do we get? This thing is less than S. And now this is a non-negative real number. This is a non-negative real number. I can not multiply, but raise both sides of this equation to the nth power, and I get the absolute an is less than S to the n. So I get a bound on an, and the bound is S to the n. And S is less than 1. And so this is looking a little bit like the comparison test or the Weierstrass M test. So now, that equation is not true for all n, but it's true for all but finitely many. So what that means is then the summation of an is less than the summation of Sn, S to the n, plus some, I'm just going to call it cap f, some finite term. So where f is some finite term. So where is this finite term coming from? This equation is true for most n. It's true for all but finitely many n. For finitely many n, perhaps there are a million n for which this equation is false. Then those million n will contribute something to this summation, right? And whatever that something is, it will be finite. And so this thing is less than this up to some finite change, which is where that finite term f is coming in. So this summation is less than s to the n plus some finite term. And it doesn't really matter what that finite term is because we're only trying to assess whether this thing converges or diverges. And so here, so notice the summation of s to the n is finite. And so this thing converges. And so the original converges absolutely. And that proves the first part. So that converges absolutely. To converge absolutely just means when you stick modulus signs around these things, then it still converges. And so we get the absolute convergence of the original sequence in the case when C is less than 1. Now, what about the other case? So let's do the other case. So I'm going to erase this, and then I'm going to do the case when C is greater than 1. When C is greater than 1, we're going to use a similar strategy. So if C is greater than 1, so let's write out what that means. So then the lim sup of absolute an to the 1 over n exceeds 1, then we can find some other s in between these. So let's find some lim sup an 1 over n is going to exceed s, which exceeds 1. So s is slightly more than 1, and s is slightly less than the lim sup. Now, if s is less than the lim sup, strictly less than this value, which is the lim sup, and some infinite finite subsequence of an converges to this greater number, then that must mean that infinitely many of these terms, an to the 1 over n, exceed s. So this is not all but finitely many, but infinitely many. So for infinitely many n, what do we get? We get absolute an to the 1 over n exceeds s. Not necessarily true for all but finitely many, but definitely true for infinitely many n that this is true. So notice there's a difference here between what I'm calling for most n and for infinitely many n. So here an to the 1 over n is greater than s for infinitely many n. And then if I raise both sides to the nth power again, we get this thing is greater than s to the n. Now it doesn't even matter that, I mean, here I've got a little bit of leeway here. S to the n is greater than 1. And so the terms an do not even approach 0. And if the absolute values, if the modulus of these things don't approach 0, then the terms themselves don't approach 0. And so it follows then that this thing diverges. So the spirit of the root test is, well, the way I remember it is we pretend that this thing, we pretend that we kind of want this thing to be a geometric series. We want it to be a series so that an is equal to r to the n, and we try to recover the value of r by first taking the absolute value and then extracting the 1 over n root. And that would be r. But for a general sequence, that's not constant. So we take the lim sup, and then that lim sup predicts in exactly the same way that r would predict for a geometric series. That lim sup predicts convergence. So this is the Cauchy root test for a series of complex numbers. And in the next video, what we'll do is we'll do the Cauchy-Hadamard test, which is a very similar test which applies to a series of complex functions instead of simple complex numbers.